Test, try number 2.
Yes.
Good afternoon, everybody. My name is Tomislav Dragičić. I'm professor here at DTU Electro, and I'm the chairperson for today's PhD defense. We have examiner team with one internal examiner and 2 externals. Internal examiner is Associate Professor Chu-Wei Wu from CE and DTU Electro. And first external examiner is Professor Ramtin Sios Hansi from Ohio State University. And another is Associate Professor Trine Krog Boomsma from University of Copenhagen. And all 3 of our examiners are online present today. Our main supervisor for the PhD student is Associate Professor Jalal Kazempour, who is physically present here today, and the co-supervisor is Professor Pierre Pinson, who is also physically present today. The name of our PhD candidate is Anna Schwele, and the title of her lecture and of her PhD thesis is Integration of Electricity, Natural Gas, and Heat Systems with Market-Based Coordination. And the host department is Department of Electrical Engineering. And now I will just briefly introduce what will happen in the next steps. So Anna will give us approximately 45-minute presentation. After which we will make a very short 5 to 10 minute break, and after the lecture and after the break we will give the floor to examiners who will ask questions in a round robin manner, and we will also save some space for questions from supervisor and potentially from the audience. This whole process should not last more than 3 hours, and after the lecture is done, 2 hours in maximum should be for the questions. So with this being said, I would like to leave the floor for Anna and her lecture. So please go ahead.
Okay, thank you, and a warm welcome to everyone joining both offline and online. Today I'm going to present my PhD thesis with the title Integration of Electricity, Natural Gas and Heat Systems with Market-Based Coordination. And this thesis sums up the work I've been doing over the last 3 years, and the work was supported and funded by the core project. Okay, sorry. So first of all, the share of renewable sources in the energy mix is steadily increasing, especially here in Denmark, so that in the power system last year, 50% of the total electricity consumption was covered by renewables, especially wind power production. At the same time, natural gas and heat systems are becoming greener too. Biogas production and its injection into the gas grids are on the rise. And also in the heat sector, renewable heat production is increasing, mostly via biofuels and electrification. And at the same time, the heat, most of the heat consumption here in Denmark is supplied by district heating. So this higher share of renewable energy production by weather-dependent sources brings uncertainty and variability into the system, and that challenges the way energy systems are currently operated and increases the need for operational flexibility. And by operational flexibility, we refer to the ability of a system, the power system, to adjust its output in response to a change in renewable power production in order to maintain balance of demand and supply at all times. And there are several potential sources of flexibility in the power system, for example, demand response, different electricity storage options, or controllable transmission lines, for example, HVDC lines. And also often units at the interface with other energy systems can provide flexibility. For example, gas-fired units usually compensate for the variability of uncertain wind power production thanks to their fast start and ramping capabilities. Heat pumps, on the other hand, can provide electricity demand side flexibility, and also combined heat and power plants, the so-called CHP units, can provide flexibility by varying their heat power output ratio. All these units yield both physical and economic interactions that couple these systems to become more and more interdependent. And apart from that, the gas and heat networks can also provide additional flexibility because of their ability to store energy in their networks. This is due to the slower time dynamics of heat and gas flow compared to power flow. And it can be an advantage since, unlike in the power system, demand and supply do not have to be balanced instantaneously. The main advantage of energy system integration as a provider of flexibility is that it makes use of already existing energy infrastructure. So there's no need for additional investments. And it provides the opportunity to decarbonize all energy sectors. We see several challenges towards unlocking the full potential of energy system integration in order to reveal and exploit the existing cross-carrier synergies and the flexibility from assets and the interface. Stronger coordination among the power, gas, and heat sectors are crucial. And coordination can be any mechanism or effort that tries to optimize the interactions between the systems that arise from these energy system couplings and interdependencies. Second, market compatibility needs to be ensured. Currently, each energy sector is operated separately and sequentially and as if independent from each other despite their interdependencies. In Denmark, for example, the heat system is dispatched before the electricity system based on estimated electricity prices. And then the electricity system is dispatched before the gas system based on estimations of natural gas price and fuel availability. This uncoordinated setup limits the use of cross-carrier synergies and the flexible assets at the interface of the systems. And finally, the increasing uncertainty of renewables will propagate through the systems and eventually affect the operation of all systems. And our research questions target these three challenges. First, how much value, and value in terms of reduced system cost or increased social welfare, can coordination of integrated energy systems bring? And then based on that, how can we harness this added value and how can we achieve coordination under the current market framework? Coordination options range from the disruptive choice of redesigning towards an integrated energy market to less disruptive solutions that preserve the current market framework with separate and sequential clearing of markets. Full coordination requires either a single central system operator or perfect information exchange and timing among the systems. Although full coordination cannot be implemented in practice, it is still useful as an ideal benchmark. More practical coordination schemes that preserve the current framework can be realized by improving the information exchange among the systems and increasing the awareness. We call these soft coordination, and this can be, for example, introducing market products, introducing new bidding formats, or introducing new market players. And finally, how can we model and account for uncertainty and also its propagation among energy systems? To answer these questions, we can combine a multidisciplinary set of tools. First, market-based coordination should enhance the information exchange among the systems, and game theoretic models and equilibrium models can be used as market simulation tools. Then optimization models can aim at revealing all potential flexibility from multi-energy coordination with a focus on network flexibility. And we can use convexification approaches to describe the physics of energy flow dynamics. And stochastic models can accommodate uncertainty and account for the uncertainty in the decision-making process. So to sum up, the objective of the thesis is market-based coordination of power, heat, and natural gas systems under uncertainty. And to achieve that, first we look into the physics of energy flow dynamics and focus on network flexibility from heat and gas networks. And we develop dispatch models that account for these energy flow dynamics. And then we use convexification approaches to be able to solve these holistic energy models efficiently and derive, if not feasible solution, at least lower bounds on the total system cost. Next, we need to accommodate uncertainty in the coordination and find ways to mitigate uncertainty and the propagation of uncertainty. We use both scenario-based approaches and also distributionally robust optimization. And we propose an uncertainty-aware coordination mechanism with a focus on enabling flexibility from all sectors to provide operational flexibility. And then we come up with a market-based mechanism to improve the coordination. Specifically, we propose financial instruments to improve the exchange of information among markets. And this thesis and also the presentation summarizes 4 publications and 1 peer-reviewed conference contribution, 2 journal articles that have been published, and 1 journal article that is currently under the 2nd round of reviews. So after this brief motivation, I'm going to discuss first the ideal benchmark models of full coordination, first in a deterministic and then in an uncertainty-aware manner. And afterwards, I'll show our proposed soft coordination approach, which includes financial instruments in power and gas markets. And finally, I conclude and give some ideas about future directions for research. Note that we include the heat sector in the deterministic benchmark model, while after that we'll concentrate on power and gas coordination only. So let's recall that full coordination is an ideal benchmark that assumes either a single central system operator or perfect information exchange and timing among the systems. And the full coordination model aims at revealing the maximum potential flexibility from heat and gas networks for the power system. On the gas side, there's potential of storing energy in the pipeline, since inflow of gas into the pipeline does not necessarily have to be equal to the outflow. This concept is called Linepack, and Linepack flexibility acts like a buffer that can be filled first and then emptied at a later time. In district heating networks, the mass flow rates in the pipelines directly impact the time it takes for the heat to propagate through the pipe, so that this time delay of heat propagation allows us to temporarily decouple the heat production from the heat consumption. And especially when both inlet temperature and mass flow rates are control variables, this allows us to optimize the energy that can be stored in the district heating network. In general, it's quite complex to holistically model the integrated energy systems while accounting for the specific flow dynamics of each specific energy network. So we use approximation and convexification approaches towards computational efficiency and also market compatibility. So let's look at the model. The proposed combined multi-energy dispatch aims at minimizing the total operational cost of power, heat and gas systems. And it's subject to operational constraints in all sectors. And then we have coupling constraints that describe the interdependency among the systems, and especially how the units at the interface link the 3 systems together. While the objective function and decoupling constraints can be modeled in a linear way, AC power flow constraints are non-convex. However, under these 3 assumptions, neglecting reactive power and neglecting losses, the linearized DC power flow equations can be used as an approximation. The gas flow can be modeled according to its steady state flow equation, the so-called Weymouth equation, which relates the pressure points at both ends of a pipeline to the flow along the pipeline. Furthermore, we include Linepack, that is the energy that can be stored inside pipelines, which allows for varying in and outflows. And note that we need binary variables in order if we want to account for varying flow directions in the gas network. And also the Weymouth equation is a piecewise quadratic equality constraint and therefore non-convex. In the district heat network, there are parallel supply and return pipelines, and both mass flow rates and inlet temperatures can be control variables. We need binary variables in our model to account for the variable time delay of heat propagation throughout the pipe, which depends on the mass flow rate. And then there's the Darcy-Weisbach equation, which, similar to the Weymouth equation, relates the pressure drop along a pipeline to mass flow rates. And it's a quadratic equality constraint, and that's again non-convex. And we propose to use convexification strategies to handle the non-convexities that arise from energy flow dynamics. So first we assume that we know the flow directions in the gas network, and then the original quadratic equality constraint that relate the pressure drop to flow rates, and both the Weymouth equation and the Darcy-Weisbach equation describe the surface of a cone as shown here. And we propose to convexify them by relaxing them and extending the feasible space to include the inside of the cone as well. And we end up with second order cone constraint. In the heat side, we also have bilinear terms for mass flow rates and temperatures, and they can be relaxed using McCormick envelopes. Next, when we do not assume that we know the flow direction in the gas network, but we allow for varying flow directions, we cannot simply relax the quadratic equality constraint because of resulting bilinear terms. So we propose a new convexification method that uses McCormick relaxation on top of the quadratic relaxation, and we end up with a mixed integer second order cone model. And we can compare this approach to another approach that has been proposed in the literature. It's an outer approximation based on Taylor series expansion around fixed pressure points. And this basically models a set of linear inequalities that then describe planes that are tangent to the cone. When we look into some results, a small case study with all three systems, assuming unidirectional gas flow, we model this as a mixed integer second order cone program. And here you can see that the total amount of natural gas and heat supplied and consumed over the 24-hour time horizon is not necessarily balanced. So we can see the shaded area describe the amount of gas and heat that can be stored in the pipelines. And thus the networks act as a virtual electricity storage with charging and discharging options. When the next graph shows the total operational cost of the integrated system under varying levels of wind power penetration, which we define as the total installed wind capacity divided by the maximum electricity demand. And you can see that the costs are decreasing with increasing levels of wind penetration. And furthermore, when we compare our approach here, the green line, to another model that does not account for the flow dynamics and the storage effects of the networks, we can see that including the flow dynamics results on average in a 2% decrease of cost. And lastly, when removing the heat system from our analysis and focusing on the gas and power networks, but this time allowing both bidirectional flow and Linepack as degrees of freedom from the gas side, we compare the two convexification approaches I discussed, the relaxation based on McCormick relaxation and quadratic relaxation, and the approximation, which is a linear approximation. And we can see that those two approaches lead to slightly different results in the Linepack. And we can also compare them based on cost. And here we see that when comparing the operational cost to the case neglecting Linepack, here the green line, that both the relaxation in blue and the linearization in red lead to a cost reduction on average 2 and 1%. And when comparing to the case of an ideal electricity storage, so storage with infinite capacity and infinite charging and discharging abilities, we can see that accounting for Linepack is equal to cost savings similar to, on average, 25 or 13% of the case of an ideal electricity storage. So when we want to make use of this network flexibility that we just showed for the power system, we do not only need to consider the energy flow dynamics, but also be aware of uncertainty. So next, we'll concentrate on the power and gas system and extend the full coordination model to account for uncertainty and become uncertainty aware. With natural gas-fired power plants and the gas network and Linepack as sources of short-term flexibility for the power system, the growing interdependence of power and natural gas systems causes short-term uncertainty from wind power production to propagate to the gas side. And weather-dependent renewable power production is highly uncertain, so we model this uncertain wind power injection as a single point forecast and a forecast error omega. This omega characterizes the uncertainty and follows an unknown probability distribution. So now we want to extend the full coordination model here in a compact form to become aware of forecast errors resulting in a stochastic program with stochastic variables x tilde that include recourse actions dependent on the forecast error. So how should we accommodate uncertainty in our model? There are different alternatives. One is stochastic programming. And this stochastic programming optimizes in expectation when the uncertainty can be sufficiently characterized by a set of scenarios that can, for example, be generated via sampling techniques, and it recasts as a scenario-based approach. However, since usually a high number of scenarios is necessary in order to properly represent the underlying probability distribution, this may become quite computationally expensive. Another approach is robust optimization. Here we try to encapsulate the underlying distribution of uncertainty in a set, the so-called uncertainty set S, and then optimize against the worst case in the uncertainty set, while ensuring feasibility in all cases. And then the results might be overly conservative with respect to the given uncertainty set S, and also it's a challenge to build an uncertainty set when we do not know the probability distribution omega. And since the true distribution of uncertainty is not known, uncertainty should be modeled in a data-driven way. So we want to utilize data to characterize uncertainty without having to make strong assumptions on the true probability distribution. And we propose to use distribution robust optimization. And here what we do is we take available historical data, our training samples, and then instead of constructing a single distribution that could approximate our data, what we do is we construct a whole family of distribution that can all explain the data that we see. We call this set pi, the ambiguity set, and distribution robust optimization now optimizes in expectation against the worst case distribution in this ambiguity set. And note that if the ambiguity set is very small, so that it only contains one probability distribution, distribution robust optimization basically reduces to stochastic programming. And on the other hand, an ambiguity set can also be selected in a way so that distribution robust optimization becomes robust optimization, so that this approach, distribution robust optimization, generalizes stochastic programming and robust optimization. And we now propose a data-driven dispatch for power and natural gas systems. And it is key to properly build the ambiguity set first. And the size of the pi can be seen as a degree of freedom for the system operator to tune the conservativeness. And the two main methods to build such an ambiguity set is a metric-based and moment-based. We focus on moment-based. So we estimate the empirical mean, vector mu, and covariance matrix sigma from historical data. And then the moment-based ambiguity set pi here is defined as all probability distributions with the same first and second order moments, mu and sigma. And pi then contains the family of distributions with same first and second order moments. And without loss of generality, we can assume that the mean of wind power forecast errors is 0. However, the distributionally robust optimization problem is intractable due to its infinite dimensional nature. So we need to take several more steps to reformulate it in a tractable way. First, we choose to model recourse actions for real-time adjustments as affine policies. So the stochastic variable x tilde is expressed as the sum of tentative day-ahead schedule and a linear response to uncertainty, which is modeled as a function of the uncertainty omega and participation factor alpha. And this participation factor alpha determines the share each flexible unit provides towards the mitigation of uncertainty, so that the response to deviations because of the wind power forecast error is divided among flexible assets according to participation factor alpha. So now the central system operator assigns both the tentative day-ahead schedule and affine policies to flexible assets. And now it is important that the recourse actions from gas-fired units bring demand fluctuations into the gas side. So uncertainty propagates from the power to the gas side. And we need to translate these recourse actions by gas-fired units to response by flexible assets from the gas system. And both gas suppliers and Linepack, so in the gas network, can react. And for gas suppliers, we define participation factors beta, which depend on alpha through the fuel consumption of gas-fired generators. And then the response by the gas network assets is not straightforward to model because of the non-linear flow dynamics. So as a simplification, we model the response by the gas network also as affine policies, namely for the change in pressure points, the change in flow, and thus also the change in Linepack. So that gamma and rho can now be seen as auxiliary variables that translate alpha to the gas network. And finally, these affine policies can be interpreted as market products, so-called policy-based reserve products, and they enable a coordinated response of flexible assets, not only in the power side, but also in other from the gas network assets. So yeah, in this way, we try to bring Linepack flexibility from the gas side to the power system. And with the moment-based ambiguity set with zero mean and these affine policies in hand, we can now reformulate our objective function inequality constraints analytically by separating uncertainty dependent and independent components. However, the inequality constraints cannot be handled that easily. So we formulate all operational limits as individual distributionally robust chance constraints. And each chance constraint needs to be satisfied for all distributions within the ambiguity set with a confidence level of at least 1 minus epsilon. And epsilon here is predefined violation probabilities that can be chosen as risk tolerance or risk preference. And then we can approximate the probabilistic constraints by applying Chebyshev's inequality and rewrite them as second order cone constraints. So we end up with a finite dimensional tractable second order cone program. when we look at some results of a small case study with 1,000 wind forecast error scenarios that are used to estimate the covariance matrix sigma, we can see here that gas-fired generators in purple are the main providers of flexibility in the later hours of the day. And this volatility of gas demand from gas-fired generators can be partly mitigated by Linepack, and then also response from gas suppliers is required, especially in the later hours of the day, as we can see here. Finally, we perform out-of-sample simulations using a test data set for the wind forecast error scenarios that is different from the one we use to estimate the covariance matrix. And however, we do not perform re-optimization, we only do projections with fixed tentative day-ahead schedules and fixed affine policies. And then we compute the violation probability for individual chance constraints for different confidence levels 1 minus epsilon. And here we can see that for lower violation probabilities in red, that the day-ahead dispatch cost in blue increase. So there's a trade-off between the system cost and the violation probabilities or risk. So for the next part, I want to talk about soft coordination approaches. Recall that these coordination approaches preserve the current market framework while trying to enhance the exchange of information and the awareness among the sectors. And we propose financial instruments to help as coordination tool in power and natural gas markets. So let's recall that energy systems are dispatched sequentially on 2 main trading floors. Day-ahead dispatch takes place 12 to 36 hours before operation based on deterministic forecast of uncertain wind power production. And there is asynchronous timing between the power and gas markets, so that power market is cleared before the gas market based on estimated natural gas prices. And then closer to real time, any imbalance that occur are cleared in the real time markets. To model the setup in a compact manner, first the electricity market clears in day ahead based on wind power forecasts and estimated natural gas prices. And the market operator aims at maximizing the social welfare. And when we assume that demand is inelastic to price, this can be, this is achieved by minimizing the operational cost. And we need to take into account the operation limits as well as ensuring balance of demand and supply. And then for given day-ahead schedules of gas-fired units translated into a gas demand, the natural gas market clears in day ahead. Again, we model this as a cost minimization problem. Note that the dispatch of gas-fired units here, X star, is treated as a fixed input into the natural gas market clearing. And then while the wind power forecast in day ahead is a single point, the actual wind realization in real time is uncertain. And we represent this here as a finite set of scenarios. So that then for given day ahead schedules, once the wind realization occurs, the real-time power market clears any imbalances for any scenario omega. And again, this is represented as one cost minimization problem for each scenario. And finally, for given gas demand adjustments and day-ahead schedule, the natural gas market is cleared again for each scenario. Note that there's no coordination in this current sequential setup between the power and gas markets or between the day-ahead and real-time trading floors, so that the electricity market in the day-ahead is unaware of the gas sector and unaware of the real-time stage. And we propose now to include virtual bidding for improving the awareness both between the sectors and between the trading floors. Virtual bidding is a purely financial instrument And it allows market players, including suppliers, generators, or purely financial traders, to perform arbitrage based on anticipated price differences between two trading floors in energy markets, for example, day ahead and real time. And they do not have to physically consume or produce energy. We distinguish between two types of electricity of virtual bidders. First, the explicit virtual bidder has no physical assets. So if an explicit virtual bidder buys 1 megawatt hour in day ahead market, she then has to sell the same amount back in the real time market. So that her positions in day ahead and real time need to even out to zero. And her payoff is equal to the difference between the day ahead and the real time market prices times the amount of virtual trade. The second type of virtual bidder we include can blend virtual bids with physical bids. And so an implicit virtual bidder has some physical assets to back up their bids. Those implicit virtual bidders can place bids that go beyond their capacity as long as the resulting position in real time is within the operational limits. And especially gas-fired units may find it profitable to forgo the market and dispatch themselves outside the market if they can better represent their technical constraints, or they have a better estimate of the real-time prices and also of the natural gas prices and fuel availability. We include explicit virtual bidders in our model, assuming they are price takers. So unlike the system operator who sequentially solves deterministic optimization problem, these explicit virtual bidders are profit maximizers, so they solve a two-stage stochastic problem. And we assume that they can perfectly anticipate the distribution of real-time prices across all scenarios. And then the amount they trade in day ahead has to be exactly canceled out in real time under any scenario. And note that the virtual bids here, V, are treated as exogenous parameters in the market clearing constraints. So that these optimization problems now are interrelated and construct an equilibrium problem. Similar, when we allow gas-fired units to act as implicit virtual bidders, we assume that they can perfectly anticipate the day ahead and distribution of real-time prices in both electricity and natural gas markets. And their dispatch decision is then treated as fixed input into all market clearing problems. And they can now act as a coordinator between both power and gas markets and day ahead and real-time stages. So to simulate this market, we include the market clearing problems in day ahead for electricity and for natural gas. And then in the real time, we include market clearing for each scenario that might occur, both in electricity and natural gas. And these are deterministic optimization problems that can be solved sequentially. And now we add explicit virtual bidders in both the power system and the natural gas system. And we also allow gas-fired units to act as implicit virtual bidders. And since these optimization problems now are interrelated, we need to solve all optimization problems simultaneously as an equilibrium. And from a game theoretic perspective, this becomes a non-cooperative game where the players interact both on their payoffs and the strategy set, since the dispatch of virtual bidders is treated as a fixed input into the market clearing constraints of market operators. This is defined as a generalized Nash equilibrium. And under some assumptions, we can prove existence of a solution. However, we cannot prove uniqueness, so there might be multiple solutions. to this model, and mathematically we can formulate it as a quasi-variational inequality, or recast it as a mixed complementarity problem, when replacing each optimization problem by its Karosh-Kuntaka optimality conditions. And then the equilibrium model is solved by considering the KKD conditions of all optimization problems simultaneously. In order to evaluate the impact of virtual bidders, we compare the proposed mechanism to a full coordination model, which is an ideal benchmark, and we model this as a stochastic market clearing model, where a central system operator minimizes the total expected system cost. Note that this is not compatible with the current market framework, and also there are some desirable market properties missing. For example, the merit order is not preserved in day ahead. Analytically, we can show that including explicit virtual bidders, both in the power market and the natural gas market, results in price convergence in expectation. So the day-ahead market prices are equal to the expected real-time prices. And another result that we can see this that under some conditions, even though the generalized Nash equilibrium problem we propose is not equivalent to the ideal benchmark of stochastic optimization, under some conditions, the outcome of these markets can actually be the same when we allow all gas-fired units to act as implicit virtual bidders. And finally, we want to look at some numerical results of a small case study. And here we can see in the case of no coordination on the left, the bar on the left-hand side, this gives us an upper bound on the total expected system cost, while the ideal benchmark of stochastic market clearing provides us with a cost reduction of 7%, which is the lower bound. And then we can see that the three options of soft coordination with explicit virtual bidding only, implicit virtual bidding only, as well as both explicit and implicit virtual bidding, can help approximate this ideal benchmark. And this implies that financial instruments can bring market efficiency and help reveal and exploit the existing flexibility in the systems while preserving the current market framework. So it's interesting to see that some players acting as expected profit maximizers and having high quality information can be beneficial towards coordination of energy markets. So to conclude, first, our multi-energy model reveals the maximum potential network flexibility that can benefit the power system. And then uncertainty propagation from the power to the gas side can be mitigated using affine policies. And they can be looked at as reserve products that make flexibility from the gas network available to the power side. And lastly, financial instruments help improve the coordination between energy sectors and trading floors. So to sum up, coordination of energy carriers is an inexpensive solution to provide operational flexibility in the power system. And for future directions of future perspective, the next step towards coordination of energy sectors will be to ask how to monetize the network flexibility that we showed, and how to price this flexibility service that gas and heat network operators can provide to the power system. And this requires proper pricing, and then the profit that the network operator can make from that. How can we allocate and distribute that profit? For example, one could think of financial rights similar to financial transmission rights or virtual storage rights in the power system. And second, can we think of additional market products that make flexibility available across energy carriers with proper price signals? not only for operational purposes, but also to incentivize adequate investment in flexible assets at the interface of the energy systems. And lastly, since we showed that uncertainty propagates from renewable-based power systems into the other energy sectors, it's going to be interesting to investigate first how long does it take for the uncertainty to propagate, and how much delay is in there, and also if we have potentially harmful propagation of uncertainty, is the stress in one system going to affect the other system? And for that, one would need a comprehensive analysis of systemic risk, which is any risk that threatens not only single assets, but the entire system. And we need to ask if gas and heat systems are resilient enough against harmful power side uncertainty. Yes, and with that, I want to thank you for your attention.